So contingency tables are a really nice way to display how your data is separated into certain categories. So for example, this example we have here below, we're looking at a number of people that were interviewed and asked two things. If they had a speeding violation and if they also used a cell phone, or if they didn't have a speeding violation and if they also used a cell phone. So basically kind of two yes or no questions. Have you had a speeding violation? And are you a cell phone user? Do you have a cell phone? So what we're seeing here are these four numerical categories. 25 people answered yes to both. Yes, I have a cell phone. Yes, I have a speeding violation. 280 people said, yes, I have a cell phone. No, I don't have a speeding violation. 45 said, yes, I have a speeding violation. No, I don't have a cell phone. And 405 said, no, I don't have a cell phone. No, I don't have a speeding violation. All right, let's look at this and find these probabilities that we're asking for. So note here that I'm kind of mixing. I didn't call each thing an event letter. Okay, I wrote P of a person being a cell phone user. Okay, you can call these events letters if you want, if that helps you kind of organize this a little more. Maybe this is V for violation and N for no violation, or NV. I don't like using multi-letters for my things, but if that helps you keep them separated, we could do that. So here, this would be the probability of a cell phone user, or P of C. The way we find this is the number of cell phone users out of the total number in the study. So this table we have in front of us doesn't already have these separated, but we need to know the total number of people in the study in order to know what these fractions will be out of. What we're really doing is we're kind of imagining that we have this pool of people, all the people in the study. And we're saying, what's the probability of selecting a person that meets this requirement? Well, in order to know that, we need to know how many cell phone users there are. Well, we know 25 had a speeding violation, 280 didn't, but all of those are cell phone users. So when you have a contingency table, it's really good to just add a column for the total, as well as another row for the total. It's not going to be the most pretty, but we're going to just draw onto our contingency tables, and this will be given to you. Sometimes it wasn't here, so we have to create it. So we would say 25 plus 280, and that's going to equal 305. That's the number of cell phone users. If I go across, that's the total number of cell phone users. All right, the total number of non-cell phone users, people who don't have a cell phone, is 45 plus 405. All right, or 450. The total number of people who had speeding violations is going to be 25 plus 45, or 70. The total number of people who didn't have speeding violations is going to be 280 plus 405, or 685. And then the total, the number of people in the study altogether can be found by either adding 305 and 450 to get 755, or by adding 70 and 685. We could add a cross instead, and either way, we'll get the 755. All right, so with this contingency table now fully set up, it's easier for us to pull probabilities. The probability of a cell phone user is the number of cell phone users divided by the total number of people in the study. So 305 out of 755. We could put that into a decimal, but honestly, I'm okay if you just leave it there. If you are doing your homework online, it's going to ask you for a decimal. So just put it in a calculator and write that corresponding value. The probability of finding a person that has had no violation. Well, that's the number of people who have had no violation out of the total number of people. So I'm going to go to my no violation. 685 people have had no violations. out of 755. Right, the probability of someone that has had no violation and was a cell phone user. So now we're not looking at the totals because we're meeting two requirements, no violation and a cell phone user. These are all the no violation people. And these are all the cell phone user people. So the people that meet both requirements are right here. Those 280 people meet both requirements. So that's 200 probability of no violation and cell phone user is equal to 280 out of 755, still out of our total number of the data set of the study. All right, the probability of a person having a cell phone or has had no violation. Probability of a cell phone or no violation. A couple ways to go about this. We can remember that we have a formula that goes with this. For an or statement, it's the probability of the cell phone plus the probability of no violation minus the and statement, probability of cell phone and no violation. So probability of cell phone, we already calculated, but we could go back to the chart if it was a different problem. All the cell phone users out of the total, 305 out of 755, plus the no violations, that's 685 out of 755. Divided, minus, my bad, the and statement. So again, cell phone user and no violation repeats at that 280. So minus the 280 out of 755. You notice these have a common denominator here. So I can just add the numbers 305 plus 685 and then subtract 280 and we get 710 out of 755. The other way to look at this is to look at your chart. If we want C, cell phone users or speeding violations, we would count all of the cell phone users. That's where this number comes from. All of the no violations, that's where this number comes from. But you see that by counting these, we have counted that 280 twice. It got counted on the first round and it got counted again. That's why it's being subtracted out because it only gets to be counted the one time. That's kind of a visual representation of how that addition rule or that or statement formula works. All right, and finally, we have the probability of a conditional probability with a contingency table. All right, we have two approaches for this. So this is a long video, I apologize. But the one approach is to use our contingency table and kind of think through it logically. I mentioned earlier that we could imagine we had a pool, all right, with all of the people in our study in it. So that had all 755 people in it. And we were randomly selecting someone. Well, out of these, for cell phone users, there were 305 different ways to select a cell phone user. If we're given a piece of information, we're told something's definitely true, the probability of selecting a cell phone user given that we know they had a violation. So they definitely had a violation. Then when I'm looking at my pool of people, I'm going to say, hey, everyone who did not have a violation, get out of the pool. I'm narrowing down my search because I know that that given piece of information is true. So we narrow down the search, meaning that it's not going to be out of 755 anymore. Now, the only people left in the pool are the people that had a violation or did not have a violation. That had a violation. So the only people left in the pool are these 70 people right here. Okay, I kick everyone else out because I know I'm given that they had a violation. So it's going to be out of 70 instead of out of 755. This is the given information. We know they have a violation, so everyone else gets kicked out. All right, now out of the 70 people still in the pool, how many ways could I select a cell phone user? Well, I look at those 70 people, there were 25 that were also a cell phone user. So out of those 70 people, there were 25 that are a cell phone users. There's 25 different ways to select a cell phone user. So if you're given the contingency table, I feel that that's an easier way. These are the cell phone users. I feel that's an easy way to find that conditional probability. But let's say you're more of a formula person, okay? We know the formula for this, the probability of a cell phone user given that they have a violation is equal to the probability of a cell phone user and a violation divided by the probability of having a violation, right? That's the formula or the mathematical approach. Well, let's pull the and statement, cell phone and violation. Cell phone user and violation. That's 25 out of 755. Okay, because that's not a conditional probability. That's just the and statement there. Sorry, I already forgot. Cell phone user 25, my bad, out of 755. That's the and statement. All right, small fraction over the probability of having a violation. So standalone, having a violation, there were 70 out of the 755. All right, if you remember from your algebra days, if you haven't visited that in a long time or maybe never seen it, that's okay. Okay, I'm not going to ask about that. But when you have a fraction divided by a fraction, we could rewrite it if we wanted. 25 divided by 755 divided by 70 over 755. You can instead multiply by the reciprocal, meaning this is the same thing as 25 over 755 times 755 over 70. You'll see that those 755s cancel out, and this is the same thing as 25 over 70, which is exactly what we had when we went through that logical approach to get to that same place. All right, just to give you one more conditional probability here, I'm just going to do the logical approach. I want the probability of no violation given that they were not a cell phone user. Well, then that given information again goes on the bottom. So how many ways or how many people are left in the pool when I kicked everyone that had a cell phone out? Because we want only non-cell phone users. So not a cell phone, I kick everyone else out. There's 450 people still in the pool because this is now the only row I'm looking at for this problem. I know they don't have a cell phone. So everyone except those 450 people get out. No cell phone. All right, now out of those 450 people, how many had no violation? Because again, that's the probability we're looking for. So out of those 450 people, how many had no violation? Well, that's going to be the 405 there. So 405 out of 450. Thanks for sticking with me. I know that one was a little bit longer.